Hello everyone, I'm Melissa, an onboarding engineer at SkyCiv. Welcome back to our series on the ACI 31819 strip footing design calculator. In my last video, I walked through this calculator's features and functionalities. Strip footings are important in structural design because they support continuous loads from walls and distributes that load evenly. Today we will be diving deeper into footing stability and explore the importance of stability checks, the principles behind them, and how they're performed in the ACI 31819 strip footing design calculator. Stability checks are critical in strip footing design because they ensure the footing is stable under the applied loads. They prevent excessive settlement, overturning, and sliding failures, and also they're important to meet the ACI 31819 and geotechnical engineering standards. The 4 stability checks performed in this quick design calculator are maximum eccentricity, soil bearing capacity, overturning safety, and sliding safety. In this example, I have a 5-foot wide strip footing. Here I entered in the footing properties as well as the concrete properties and the reinforcement properties. I also have a 9-inch wide wall on top of my strip footing, and my allowable bearing capacity is 7 KSF. I have an axial dead load of 25 kips per feet, and I have my wall live load bending moment and shear. And then you can manipulate the graphics settings. I will go ahead and run this calculator. All right, looks like we have all passing results in my output summary. I downloaded a PDF of my report by clicking this PDF report button. So let's take a closer look at the stability checks in another tab. Let's start with the maximum eccentricity check. The maximum eccentricity check ensures that the resultant force falls within the middle third of the footing to prevent uneven pressure distribution. The formula used is eccentricity equals the absolute value of the applied moment over the applied vertical force. So here we use M full over P full. The maximum eccentricity should be within B over 6, where B is the footing width. So we have a 5-foot wide footing, so 60 inches divided by 6 equals 10 inches. This matters because if the eccentricity is too high, part of the footing may lift off the soil, leading to instability. But this calculator verifies that the maximum eccentricity does not exceed the maximum allowed eccentricity, which you can see that E, the maximum eccentricity, is less than or equal to the maximum allowed eccentricity. Moving on to the soil bearing pressure check. The soil bearing capacity check ensures that the applied pressure does not exceed the allowable bearing capacity of the soil. If the applied pressure is too high, excessive settlement or bearing failure can occur. So how the calculator works is that the user provides the allowable bearing capacity of the soil. So I entered in 7 KSF as the allowable soil bearing capacity. Typically, that's obtained from geotechnical reports. The calculator evaluates the critical service load combination for the maximum soil stress. The formula for Q max, the maximum soil stress, combines the axial load P full over A, where P full is the applied service load and A is the footing area, and the effect of the moment M full considering eccentricity is added to determine the maximum stress on the soil. So 6 times M full over B squared times L, where B is the width of the footing and L is the length, which here we just have 12 inches. So we're just checking 1 foot length. So from this example, we get a Q max of 0.035 KSI, which is about 5 KSF. The calculator compares Q max to the allowable bearing capacity. If QA is greater than Q max, the check passes, ensuring the soil can safely support the applied loads without excessive settlement or bearing failure. So as you can see in the report, the maximum soil stress is smaller than the bearing capacity, so we get a pass. Continuing to the overturning safety check. The overturning check ensures that overturning moments do not cause the footing to tip over. The formula used for the overturning safety factor is the numerator is the moments resisting overturning from dead weight, soil pressure, etc. In the beginning, I did not toggle on to consider the soil above the foundation or the footing weight, so you can see that these are 0. And the denominator are the moments trying to overturn the footing, so from the wind or seismic forces, etc. The minimum safety factor for sliding was a user input, which I input as 1.5. Typically, the minimum overturning safety factor should be greater than or equal to 1.5. This overturning check is important because if overturning safety is too low, the footing may fail under lateral loads. The calculator has the user input the minimum overturning safety factor and checks it against the overturning safety factor. As you can see in this calculation, for the overturning safety factor, we get 3,125. So that is just noted as greater than 1,000. And again, our minimum safety factor is 1.5. And as you can see, the overturning safety factor is greater than 1.5, so the foundation is safe against overturning. Lastly, let's move on to the sliding check. Sliding safety checks ensure that the footing does not slide horizontally due to lateral forces. The formula used for sliding safety factor is the resisting forces from the soil friction, keyway, or passive resistance over the applied horizontal force from wind, seismic loads, etc. In this sliding safety factor equation, we have the axial dead load plus the footing and soil weight. Again, we have 0 because I did not toggle that on to consider the soil weight and the footing weight, and multiplied by the tangent of the foundation soil friction angle, which was also a user input, over the maximum shear force. I did not enter a value for the wall, wind / seismic load, bending moment, and shear, so this is 0 because it's considering the sliding check due to lateral forces. You can see we get 4,549.63 as our sliding safety factor. Again, this is just noted as greater than 1,000. I also input the minimum safety factor, typically the minimum safety factor for sliding, according to ACI 318.19, should be greater than or equal to 1.5. Why this sliding check matters is if the sliding safety is too low, the footing may move laterally, compromising the structure that it's supporting. The calculator uses the user inputs for the minimum safety factor for sliding and checks if it exceeds the sliding safety factor. You can see that the sliding safety factor is greater than 1.5, so the foundation is safe against sliding and we received a passing result. That concludes our discussion on the stability checks performed in the ACI 318.19 strip footing design calculator. As a recap, these stability checks are important because the soil bearing capacity prevents excessive settlement. The maximum eccentricity ensures uniform pressure distribution, and the overturning safety prevents the footing from tipping, and the sliding safety prevents lateral movement. I encourage you to try the ACI 318.19 strip footing calculator in SkyCiv. You can find it in the Quick Design library. If you ever have any questions on this calculator or any of our other software modules, please feel free to chat support. We will answer any questions within 30 minutes typically. If you're interested in learning more about this quick design calculator, you can watch my other videos on this topic and check out the next video for a design example. Thank you for watching.